alarm, and then you have shutdown number 1 and shutdown number 2. A couple extra devices that you have to buy, added price to the equipment. And the logic would be that if A only is high, then you've got an alarm. You probably have a problem with your skid. If shutdown 1 or shutdown 2 is high, that means that one of the, and this is not alarmed at all, then one of these has failed and you've got a controls problem. If A is high and shutdown 1 or shutdown 2 is high, then you're going to shut the machine down because logically, yeah, that went off, you've got an equipment problem someplace on the skid. You need to shut the machine down to protect it. But if you've got shutdown 1 and shutdown 2 are high, you never really know what you've got. This could have broken, and we should normally be sending an alarm, and so they would just automatically shut down with those 2. But when you've got 3 PLCs and you've got 3 sensors, how do I wire those up to make them operate? You can't wire them up this way because this is at a different setting than these 2, and this guy, as soon as this goes off, this will be ignored. Some clients said, well, just give me 3 switches for each PLC. And the instrument guys here let you know, trying to have the exact same set point on 3 different switches is extremely difficult to get. And so if you start to slowly rise into an out-of-tolerance condition, you'd have one alarm go off first, and the other 2 would not have hit their set points yet. So that PLC will be ignored. And then when the second alarm comes in, all right, now you have an agreement between these 2 PLCs, and then this one will be ignored. So it didn't seem to fit the requirements for having a higher reliable, more reliable control system. So what ended up is that every switch ended up being wired to every PLC. So it became an interesting wiring problem for the on-skid. Wires were going everywhere. And then when they finally got into the controls panels, they also had 3 times as many wires as they originally had. But you have to ask yourself, did you actually increase your reliability by doing that? For example, let's say in normal operation that pressure switch broke. Well, you would get an alarm because that sensor has failed, and all 3 are going to agree that it's failed. But you can't necessarily go and replace that without shutting your machine down, so you don't want to do that. But it's not telling you that the machine has a problem, it's just broken. But the way that the logic is set up, if you have an alarm condition, you've got an alarm and a shutdown signal, you're going to shut down, even though you only have an alarm condition. Or if this other sensor breaks, you have 2 shutdown signals, you're going to shut down because the control systems tell you to, even though your machinery doesn't require it to. So this didn't necessarily improve the reliability of the controls. So now, to try to avoid those problems, we want to get away from switches completely and just use single transmitters. Transmitter gives you a continuous signal. You always know that it's working because you can always verify that the signal that's coming out is within the anticipated range that you would expect. And if it suddenly goes outside of range or quickly goes off scale, you know that you have an instrumentation problem and not an on-skid hardware problem. And the PLCs can be programmed to look for those sudden rapid changes and alert the operators that you've got an instrument problem, and you leave the machine up and running. Now, whether you have simplex or TMR PLCs, that depends on the client. Most now are starting to go back to the simplex style because PLCs are extremely reliable now, and people are comfortable with operating them and know how to use them. The other thing about instruments for us on equipment skids is that we want to make use of proven instruments, ones that have been used on rotating equipment for great lengths of time. A pressure transmitter works well just about everywhere. You can install it anywhere you want, but not all may be suitable for 57 billion cycles like what our equipment is going to be expected to see over its life. This is a pressure indicator. You've got your pressure tap on the bottom, and you have a curved chamber that the gas goes into. And in the internal pressure of gas inside this chamber will cause it to deflect. And that deflection is then transmitted to the needle by this linkage and then by this arc gear connected to that full radius gear. This is all extremely small, extremely light. And so if this ends up in a position where it sees a lot of vibration, this part, that chamber, is not extremely stiff, and it would not take much to cause it to vibrate. And unless it's been specifically designed for high cycle fatigue, it's not unreasonable to expect this chamber to crack, which puts your process gas into the instrument and potentially into your building. So we want to make use of proven equipment. Some instruments are located in the equipment, and mechanical failure will cause machine damage. For example, on a gas turbine, one of the main things you want to protect against is high temperature on the exhaust. And some manufacturers, they actually have thermocouples in the exhaust downstream of all equipment to monitor and protect, and that works fine. If something breaks, it doesn't hurt anything. Other manufacturers have them located very close to the combustion section, so they're physically in between pieces of rotating equipment, between rotating blades. And if one of those fails, it gets passed right through the sets of blades, which causes a massive mechanical failure of the turbine section. So obviously we don't want to go and change something that's been proven in the field for something that we've never seen before, because the consequences of its failure are so catastrophic. Location can be really important. It's really important in recip services that we locate instruments properly and we spec them out properly, because that reciprocating compressors shake so much that you can't get away from it. And so having good, robust instruments is really important to be able to monitor and protect that kind of equipment. This is what the control panels for a turbine compressor used to look like. If some of you have seen some of the old Outer Limits or Twilight Zone shows, you might recognize some of these from those. Nowadays, all that is incorporated into one panel with one PLC. And the operator interface is usually now a touchscreen. Nice graphics on it, easy to change, easy to reprogram and make it more match whatever the operator requirements are going to be. So what do we see inside these control panels? Well, for a gas turbine, for example, you're going to have fuel control. You'll have process valve control for the yard valves, surge control if you've got a compressor, speed control certainly, and then for equipment protection we'll have vibration, temperatures for bearings, lube oil pressure and temperature, over speed, and then over temperature anywhere within the machines and over pressure anywhere within the machines. Okay. Generally, the higher up you go in horsepower, the more noise gets emanated from machinery. When we're looking at a 50 horsepower motor-driven pump, noise levels really aren't usually an issue. When you start getting up to a couple thousand horsepower, noise levels start to increase to where people would be concerned, and once you exceed 10,000 horsepower, then you certainly are dealing with noise levels which are going to be beyond the OSHA allowable exposure for 8 hours. And when that happens, we have to put an enclosure around it. So as for noise attenuation, it'll go over the equipment and it'll usually sit right on top of the skid, although some enclosures will be, if there's a requirement to go inside very frequently, we'll place them off the skid with approximately 3 or 4 foot of walk-around space so the operators can go inside, make sure everything is okay, and gives the maintenance crews the space to work. So if there's any internal instruments that are inside that enclosure, they need to be repeated outside where the operators can see them without necessarily having to enter every time. And we'll have windows inside so that they can view critical items. Usually they want to take a look at the oil system to make sure that you haven't no leaks have started since their last walk around. Depending on what it is that the enclosure around, we may need a fire suppression system. That's proven to be an interesting complication on a few of our jobs. We usually have them supplied by the equipment vendor, although occasionally we'll have a third party come in and fit one in the field. It's not generally over the entire train. It's usually just over the noisiest part. For a gas turbine compressor train, it'll be over the gas turbine. For a steam turbine, same thing, be over just over the turbine. Air circulation becomes an issue in that, do you want to take outside air? Do you want to take inside air? Where are you going to exhaust the air to? Usually it's warmer than it came in at. Does your building HVAC take this into account? Okay. And the enclosure may have a different area classification than the building that it's in. If you've got a generator set inside a building, the building usually won't have any process piping in it, and so the building will be an unclassified area by electrical classification. But because you may have a gas turbine inside the enclosure, that's got a fuel system which potentially could leak, so inside the enclosure it'll be a Div 2 area classification. And depending on the area classification inside-outside, if it's a Div 2 in the enclosure but unclassified outside, you want to have the pressure inside the enclosure below atmospheric so you don't have any process gas, fuel gas, leaving the enclosure into the building. If there's any air transfer, it'll be from the building into the enclosure. Whereas if the enclosure is unclassified and the building is a Div 2 area, you'd have the pressure higher the enclosure so that you always have unclassified air going into a classified area. So this is what one will generally look like. You'll have doors for access, and you'll have removable panels that you can take off for maintenance work. Some equipment comes with an enclosure that you can just go ahead and place outside, so it acts as a noise enclosure, and it's also a weatherproof enclosure as well. You can see how this enclosure sits right on top of the skid. And you can see that inside of here they've got a fire suppression system. Looks like it's either a halon or a water mist system, because they want to. This will be a Div 2 area inside the enclosure, and they need to search for fires and put in a snuffing system should they detect a fire. For us in Alaska, on this GPP job, we have a gas turbine with an enclosure around it, and we're taking air from the outside, bringing it across through the enclosure and then ducting it back out to the outside. Obviously up in Alaska it gets below freezing, and our client has dictated to us that we can't use Fe13, halon, or CO2 for fire suppression. We have to use water mist. So if we're taking air from the outside in the wintertime, it's coming in at minus 40 degrees, and we find ourselves with a fire, we're going to inject water into minus 40 degree, and instead of a fine water mist, we're going to have a fine snowfall. So we are currently trying to come up with some alternatives to either heat up the inlet air to above 40 degrees so that inside the enclosure it's always above freezing, or some other chemical mixture that we can spray in that has a lower freezing point that will do the fire suppression. So sometimes your ambient, even though your enclosure is in a building, sometimes the ambient conditions outside affect the way that you design and the way you treat that enclosure.
Just a steel box, or it's a dampener or acoustic?
The walls are usually on the outside, it's just a solid sheet metal, about 18 gauge, 20 gauge. On the inside, it may be a perforated steel panel. And between the two, you're going to have acoustic lagging, which is used for noise damping. The panels themselves may be anywhere from 2 to 5 inches thick, depending on how much attenuation you need. Okay. The goal is to have outside, in this area, 85 dBA or less, so that you can go ahead and stand next to it, have a conversation with, a normal conversation with people in the area, and not to have any special hearing protection. As you can tell, When you start looking at the enclosure, it really cramps everything inside. The ability to move is almost gone on this one. So if you ever had to do maintenance work, all of this enclosure has to be taken off. Set down, maintenance guys do their work, and then this enclosure needs to get put back on again. It's not unusual for the maintenance crew to come in, take that off, and accidentally lose it in the warehouse someplace, so they don't have to put it back on again and then take it off next time they have to do maintenance work.
On the fire suppression system that you described, is that, you said it has to be a water mist within the enclosure?
Yes. Yeah, it's interesting. Halon is no longer allowed for environmental reasons. CO2, BP flat rejects because it's way too likely to kill someone. FE13 is the fire suppression for the rest of the building, but FE13, when it comes in contact with a hot surface like the turbine shell, it degrades into its constituent components, and it no longer will serve as a snuffing agent. So that doesn't leave too many alternatives. Fine water mist is about the only one.
And that has to be introduced inside of those enclosures?
Yes. Yeah, the controls on this is going to be really interesting. We've got ventilation systems which are drawing air from the outside across the turbine and exhausting to keep the place cool. But as soon as you detect a gas release but no fire, you increase the air circulation to increase the airflow through, and that does two things. It vents whatever gas released to the outside and lowers the ratio of gas to below the lower explosive limit. But as soon as you detect a fire, you shut all of your fans off so you don't bring oxygen into it. You close dampers down to isolate it, and then you hope that you do that to try to help the fire snuff itself by not giving it any additional oxygen while you're dumping whatever your flame suppression system is on top of it. We get involved in inspection and testing of the equipment. That's all done in the vendor shops. That's where the equipment is, and they have all the ability, all the equipment to do the inspection. And what we do is we make a combination of the vendor's requirements, the industry requirements and specifications, the client inspection requirements, and any requirements that we may have. And we have the vendor add all of that to his inspection program inside his shop. And then we'll use local inspectors to go in and supervise things during the normal manufacturing process. One of the things we'll do is we call the dye penetrant check on impellers, where you spray on a red dye all around the surfaces, and then you clean it off and put on what's known as the developers, that white powder. And then where there's cracks, dye got into the crack, and then it gets pulled back out by the developer, so it makes it really easy to see where cracks are. So this works on impellers, it works on pipe, works on just about anything that might have a surface crack, but it doesn't work on subsurface cracks. Since we're concerned with high cycle fatigue, surface cracks are a real big deal with us. To find subsurface cracks and inclusions, we have to do what's known as a ultrasonic, which means that they shoot a beam of sound, ultrasonic sound, through the metal to a pickup on the other side, and you can see discontinuities in the sound frequencies and the way it gets reflected, and you can find subsurface cracks that way. Another method is magnetic particle, which means you put a magnetic field into the part, and then you put a liquid on it that has basically iron filings in it, and any break or discontinuity in the magnetic field shows up in these iron filings, and you find your cracks that way. Unfortunately, that doesn't work on non-magnetic materials. Can't see it really well, but inside here, inside the impeller, right where the vane attaches to the shroud cover here, you see there's cracks all along there too. So there was a lot of rework that this impeller had to go through before it was going to be considered acceptable for use. Now, the engineering staff at Worley-Parsons will become involved in some of the critical equipment inspection points, prefabrication meetings where we hammer out all the requirements for the inspection program for the equipment. Whenever there's a rotor balance of a relatively large rotor, we'll go and we'll witness that. Mechanical tests back in the manufacturer's plant, we'll go witness those. Performance tests and other tests, string tests, hydro tests occasionally, depending on the criticality of the equipment and the service. Okay. Final inspection, final acceptance is done by the inspection and our procurement group. We just go to make sure that it worked properly, and we can give all kinds of reasons not to accept anything, but final acceptance is done by the procurement group. Kind of gives a nice split of responsibility. So, equipment installation considerations. Remember, we really don't want external forces on our equipment. And so, the millwrights, when they're installing the equipment, we want to make sure that everything gets leveled well and is supported continuously and supported in such a way that they don't deflect the skid. So, and that really means that there's just no soft foot. And what soft foot is, we have anchor bolts that hold the skid down onto the foundation. And it's real easy to put enough torque on them to tweak the skid in all kinds of different shapes. And so to do a soft foot check, we put a dial indicator on a location near an anchor bolt, and then we have them loosen the anchor bolt. And if there's relative motion, 1 or 2 thousandths of an inch, we know that they've actually sprung the skid rather than shim it properly. So then they'll add the proper amount of shim so that we end up with continuous support and a level skid all at the same time. We want piping alignment to be done properly with field welds, and we need the pipe supports and hangers installed properly and taking the load off the nozzles to whatever the desired requirements are going to be. And we really need to have the correct equipment alignment between the pieces of equipment. So for proper piping, we generally want to get 5 diameters of straight run into the inlet. What that does is it gives a nice uniform front of gas flow or liquid flow into the pump or into the compressor. And it gives us a nice uniform velocity profile into the inlet, because the vendors don't generally know what our piping looks like, and so they do their performance runs in anticipation that they get a 5 diameter straight run in the inlet to get that uniform velocity profile coming down the pipe. And we generally look for 3 diameters of straight run out of the discharge. So on this installation here, this is a multi-stage pump. You've got this elbow coming in, and then you've got a straight run of pipe, and it's about 1, 2, 3, maybe 4. This is a little bit shy of what we would want going into the pump suction. And off of the discharge, there's only about 2 diameters, so they're pushing the limit of straight runs into the suction into the discharge. Talking with the vendors, if you show them the piping layouts that you're going to do, they can sometimes make relaxations from 5 and 3. But their going in position would always be we'd want to have 5 and 3 as a minimum. The use of eccentric reducers for liquids. If this is the nozzle of a pump, and this is the yard piping, and we reduce down to match the pump size, our pipes are almost always larger than the nozzle to have the velocities in the pipe at a reasonable level. Usually it was, what is it, 100 feet per second for fluids? How much?
Stream of the pump?
Yeah.
I usually go for like 15.
15? I think I'm thinking gas. All right, 15 feet per second, where it'll accelerate through the nozzle to about twice that. So we have piping that's larger than the nozzle, then a reducer to match. But in a fluid, in a liquid system, as you fill it up, once you get to this point, you can't fill it up any higher. The gas has no place to go, so you've trapped gas inside the upper section of the pipe. So to avoid that, you use what's known as an eccentric reducer, so that it's cut off right where that line would be of fluid, so you end up being able to fill it up all the way without any air pockets or gas pockets. Now this is what they look like. You can see it right here. This is flat on top, bulge on the bottom. This is an eccentric reducer attached to this pump suction that goes up. These pumps, I think, are used in yogurt processing, but this is the same philosophy. Strainers. Used on the suction, and usually they're used just for the first couple hundred hours of a plant operation. They're there to catch whatever didn't get caught by piping inspection before the plant was brought up. And so it's there as a last resort to catch weld splatter, weld rods, rags, wristwatches, anything else that may have been left inside the piping systems.
In your experience, do you ever see them take out the quote-unquote temporary strainers? Because it seems like they turn them into permanent installations.
There is a lot of that. Actually, I have seen a few that were brought out and left out by very conscientious people. But for the most part, they're put in at startup, and they kind of like, you know, if it's not right in front of me, I forget all about it. And it's not making me think about it because it's not catching anything, therefore I don't see any high differential pressure across it. It's not affecting the performance of my compressor that I can see, so why change something that's obviously not doing anything bad for me? But yeah, generally they are temporary. The PNIDs will identify them as temporary. 6 or 8 years later, that temporary strainer is still in that piping system.
Yeah, there's a 20-year-old PNID with a temporary strainer.
It's still in place. Temporary is a relative term. On this style, there's a bucket that gets pushed down inside. Fluid comes into the bucket, across the stream, and then out the discharge. This is known as a Y-type strainer. Your access to your straining cartridge is through this flange here. Normal process stream goes down. This is nice. It's self-draining. It's nice that they actually gave you this drain so that you could take this process fluid away rather than have it dump all over you as you try to open this flange up to get the dirty strainer out. There's a location, there's a tap up here. One thing about strainers is you don't know if they're dirty if you don't have any instrumentation to tell you that they're dirty. You can assume that they are and shut down every couple hours and look, but eventually that gets pretty old. And so it's good to have at least some kind of a pressure indicator upstream of the strainer so that you can watch the pressure change with time to give you an indication that the strainer is starting to build up dirt, crud, whatever happens to be inside of it, and it gets to a point where it's time to change the strainer out. And here, there's a flanged off stub out that would probably hold in a pressure indicator to give you that knowledge that the strainer needs to be cleaned. This is off of a compressor. It's what's known as a witch's hat. Pretty self-explanatory. But it comes off of approximately a 30-inch or 36-inch line. A huge area, so you have minimal pressure drop. And you want to have a minimal pressure drop across this for a couple reasons. One, you don't want it to have such a huge pressure drop you add excessive head requirements to your compressor. The other thing is you don't want to have such a huge pressure drop across it that it's going to collapse, and now that will go through your compressor that is trying to protect. So laydown space. It's important to allocate, but it's kind of hard to justify. You need space beside machinery so that when you pull it apart, you can put the parts down in such a manner that you know how they go back in. And the bigger the piece of machinery, the bigger the space you need. But space is money. And so trying to get a large enough space for what you need to do sometimes is in conflict with people who want to keep the price of the project to a reasonable level. Crane access is a consideration, especially for large pieces of equipment. You may be able to use carts to move parts around once you've picked them off of the machine, drop them on a cart, take them someplace else, if the parts are small enough. This is a steam turbine. And as you can tell, when they take it apart, they're spreading parts all over the ground. So having enough laydown space is real important for these guys. So that was it for the balance of the rotating equipment. I have about another, say, 10